All right. Hello guys. Welcome to another physics class. Let's just quickly wrap up our class on electromagnetism. Let's try and attempt more questions on electromagnetism before we call it, a wrap. And we'll move on to a new topic: electricity, electric circuits, static electricity, all of that. All right. So what we are going to be doing is we are going to be attempting some questions on electromagnetism, and let's see if we could test our knowledge or even come across something we've not discussed in our previous class, new concepts, what have you. All right, let's get down to business. All right. Please, I'll be getting questions from my school because, they give us trusted sources of, term questions and the like. So let's go physics, exam type, question type. Let's just focus on the topic. And the topic is, can we find electromagnetic? So we have electromagnetic field here. Alright, so let's start from the first question. Which of the following statements is true of the properties of a moving coil galvanometer? Something about a moving coil galvanometer is, there's this very strong permanent magnet inside this galvanometer to, allow high magnetic flux linkage. So the right answer here is going to be option C. They have to be a very, strong permanent magnet that, allows, magnetic flux, to, flow better. All right. The next question, they said a step-down transformer has a power output of 50 watts and an efficiency of 80%. So let's take, they give us power out to be 50 watts, and they give us efficiency to be 80%. They said if the main supply, that's voltage in, or let me call it voltage in, let me call it voltage of the primary winding. And some of this is looking really crazy to some of you guys. There's something called induction. We'll do more of this when we get to electricity though. We have heard of the word induction before. Let's say this is a coil. Now, if I put a coil in front of another coil or in the presence of another coil, right? And if, let's say, an alternating current is supplied into one coil, what happens is we are going to be having magnetic flux linking from this primary coil into this secondary coil here. Look at it. See this coil. Don't forget, when current flows, there is a magnetic field generated around the current. And this is where it gets wonderful, because the current is an alternating current. As the current is increasing and decreasing, the magnetic field coming along with the current would also increase and decrease. Which means the primary coil would generate something called a changing magnetic field, or a time-changing magnetic field. Let me go over this again. If I pick two coils, let me erase the whole thing. Now imagine I have a coil. Please permit my image or my diagram. Let's say I have a coil. Let's say this is a coil. And I connect this coil to alternating currents. What is an alternating current? It's a sinusoidal current that goes up, come back to zero, and goes negative, and come back to zero. These are alternating currents. So if I connect an alternating current to a coil, and what you know is, because don't forget, remember from our class on magnetism, that when current flows through a wire, or through a conductor, there's always an electromagnetic field. So there's always a magnetic field that is generated at current, which means as this current is flowing through this coil, there's going to be an electromagnetic field. As the current is flowing through this coil, they're going to be having an electromagnetic field generated around the coil. Did you understand it? And because this current is a sinusoidal current, or it's a changing current, it goes up, comes back to zero, and goes down. It means the magnetic field that will also be generated by the current would be a changing magnetic field. Right? So we can establish that we are going to be having a time-changing magnetic field generated in the primary coil. Are we good? Now, if I pick another coil and I just put it very, very close to this secondary coil, some of the magnetic flux would be linked to the secondary coil. How do we know this? Remember Faraday's law of induction? It told us that when I put a current carrying conductor, I put a conductor in the presence of a magnetic field, EMF is going to be induced. Yeah. If we can remember, we said there is a time-changing field generated around this primary coil. Let me call this primary coil. Therefore, if I put the secondary coil very close to the primary coil, probably not very close, like within a specified range, then what you're going to be seeing is, because this secondary coil will be in the presence of, a changing magnetic field generated by this coil, an EMF will be induced inside this coil because it follows the law of induction by Faraday. Because now this secondary coil will be in the presence, is a conductor in the presence of a changing magnetic field. Definitely, an EMF is induced in the secondary coil. This concept is something called mutual inductance. I know I should have even explained inductance here, but we'll explain more of inductance when we get to electricity. Yeah, so we'll explain more of inductance when we get to electricity. But this concept is called mutual inductance. And see this image that you see here, this is how transformers are built. I put together. This is ideally what we refer to as a transformer. Let me just quickly add this. When you see this symbol in physics, this refers to a transformer. The transformer is made up of two coils, a primary coil and a secondary coil. And what is the job of a transformer? To step up a current or to step down. You could say to step down voltage or to step up voltage, not current, basically. To step up voltage or to step down voltage. Now, when do we have a step-up transformer? We have a step-up transformer if we have more turns in the secondary winding than in the primary winding. If you notice it, we have more number of turns in the secondary winding than we have in the primary winding. Therefore, this is said to be a step-up transformer. And the opposite is going to be a step-down transformer when we have more number of turns in the primary winding compared to the secondary winding. And this is what we call a step-down transformer. This would increase voltage, while this step down would decrease voltage. Are we good? And basically, we have several types of transformer: iron core, air core, but it's not time to go into details about that right now, but you just need to understand, a step up increases voltage, while a step down decreases voltage. Something else that is really, really very important that we have to understand is what an ideal transformer looks like. What is an ideal transformer? And let me explain this. While this primary winding is trying to induce an EMF in the secondary winding. Are we together? Some magnetic flux is lost. Are we together? The magnetic flux linkage between the primary winding and the secondary winding is not going to be 100%. Something is going to be lost into the medium that is used for exchange. Did you understand it? So let's say some of the flux would be lost, would lost into the environment, isn't it? Into the medium. Right. Good. But for an ideal transformer, there is no magnetic flux lost. It means there's 100% flux linkage. None of the flux will be lost between the primary winding and the secondary winding. Are we together? So an ideal transformer is a transformer that has 100% magnetic flux linkage, or that has no magnetic flux lost. Did you understand it? During, induction. Are we together? Or during mutual induction. It depends on how you want to put it. So you understand the concept of an ideal transformer. Yeah. Now, something about transformers is, there is a relationship that we need to keep in with transformers, yeah? And what is the relationship you need to keep with transformer? The first relationship you need to understand is the EMF induced. Can I call it EMF or voltage? Let me just call it voltage. The EMF induced in the primary winding, are we together? The ratio of the VMF, sorry. So the ratio of the EMF induced in the primary winding to the EMF induced in the secondary winding will be the same as the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. So this is one relationship we need to know. So the ratio of the EMF induced between the primary coil and the secondary coil would be the same as the ratio of the number of turns between the primary coil and the secondary coil. You could also rewrite this relationship as the ratio, watch this, of the EMF induced in the primary winding to the number of turns in the primary winding, as the ratio of the EMF induced in the secondary winding. Don't forget, EMF means voltage. So the number of turns in the secondary winding. These two relationships are exactly the same. Are we good? So they are exactly the same. So we are going to be using this relationship. I don't know, maybe we'll come across something that would make us use this, but just keep that in your head. And let's go back to the question. They told us the efficiency of the transformer is 80%. And what is the formula to calculate the efficiency of a transformer? I think you should take this down. The efficiency of a transformer or the efficiency of most machines can be calculated as the power out divided by power in times 100%. So the efficiency of a transformer is basically the power out, the power that we get from secondary winding compared to the power that comes from the primary winding times 100%. The power that is fed, or the power that is gotten from the system divided by the power fed into the system times 100%. Now, if we have efficiency to be 80%, yeah, it means 80 over 100 is equals to power out over. And when we cross multiply, we are going to be having, 0.8 power in is equal to power out. Let's see this one place. We are going to be using this relationship. Right? Now, what else were we given? We are given that the main supply voltage, they said the main supply voltage is 200 volts. That's basically how do I put it? All right, they said if they said if the main supply voltage is 200 volts, calculate in the primary winding or in the primary transformer. And how do we do that? That's quite easy. Now we know that the power in is unknown, but the power out is 50 watts. So therefore I could say power in is equals to power out divided by 0.8. How did I get this? Just divide both sides by 0.8 to make 0.8 the subject of the formula. But the question is, why am I looking for the power in? Yeah, there's a formula in electrostatics that tells us that power is equals to current times what? Voltage. We need this formula to be able to find the current of the primary transformer. So let's find the power in first. So the power in, or the power of the primary transformer, is 50 watts divided by 0.8. And if you press your calculator, let me search up my calculator. You're going to be having, a minute please, 50 divided by 0.8. And we're going to be having 62.5. Therefore, the power in is 62.5 watts. Which takes us to this formula. So the power in is going to be equal to current of the primary winding times the voltage of the primary winding, which is going to be 62.5 watts equaling I times, we were told that the main supply voltage, the primary voltage, is 200 volts. 200 volts. So divide both sides by 200 to make I stand alone, and you're going to be having current being 62.5 over 200, which gives us 0.3125 ampere. Therefore, current is 0.3125 ampere. Is there any answer close to this in the question? 0.31 ampere is the correct answer. If you don't understand, rewind this video till you get it, so we don't waste much time. Okay, let me just do a quick recap. We said efficiency of the transformer is power out over power in. You have to remember this formula. And we were told that the efficiency is 80%, which means power out over power in is going to be 80%. But in the question too, we have also been given power out to be 50 watts. So I could say cross multiply and divide. I'm going to be getting power in is going to be equal to power out over 80%, which is going to be 50 watts. 80%, that's 80 over 100, gives us 0.8, which means our power in is 62.5 watts. Yeah, now we know the power of our primary winding, power of primary winding or primary transformer, primary winding. He asks us to find the current. We are given the voltage to be 200 watts. The relationship that combines power, voltage, and current is power is equals to IV. So we could say 62.5 watts is equals to current times 200 volts. Therefore, current is going to be equals to 62.5 divided by 200 volts, which gives us 0.3125 amperes. Please, do we understand this? All right. Let's go on to the next thing. The next question is, I said, power supply is transmitted at a very high voltage and a low current to Y. Well, the right answer here is to prevent overheating of the coil. And how do we know that? There's a formula here. When electricity passes through a wire, heat is generated. And there is one formula that allows us to be able to calculate the amount of heat energy generated. And the amount of heat energy that's going to be generated in a conductor that has current passing through it is going to be I squared RT. I'm sure you have seen this formula before. Yeah. And I will tell you what this formula is. The formula for energy is power times time. We know this, right? And power is equals to IV. Are we together? So these things are saying IV times time, right? But we know that voltage, according to Ohm's law, is IR. Therefore, these things are saying I times IR times T. I times I gives us I squared times R times T. And this is the amount of heat energy that is generated in a conductor with current passing through it. But what did you notice? I is squared, right? It means the more the current, don't forget, when I have a square, it doubles it. If not even double, it exponentially increases the amount of heat energy. So because I is squared in this equation, high current would means way a lot of heat in the conductor. Did you understand this? And to make up or to prevent overheating of the coil, we usually have to transfer very low currents and probably high voltage so it doesn't overheat and burn out. I believe you all understand that. So the answer for this is prevent overheating of the coil. Oh shit. Another inductance question. Given the inductor of inductance 5 millihenry, 10 millihenry, and 20 millihenry connected in series, the effective inductance is, the truth is, inductance is more of an electricity question than a magnetism question. Yeah, it's still under magnetism kind of, but you see it more under the electricity part or the current electricity part of electricity and in magnetism. So when we get to our class on electrostatics and current electricity, we're going to be doing, a detailed explanation of what inductance is and, most of the calculations you would come across under inductance. But for now, let me just give you a brief. Now, we are told to find the effective inductance. Another word you can see for effective inductance is equivalent inductance. They've been the same thing. So these two words are asking to calculate the same thing. But to calculate your equivalent inductance or your effective inductance, you have to be able to figure out, is the circuit a series circuit or is the circuit a parallel circuit? If the circuit is a series circuit, first, what is a series circuit? For a series circuit, if there are two or more machines on the same circuit, current and voltage would have to first pass through one of the machines before going to the other machine. Let me give you an example with the diagram. Let's say I have a source. Yeah? Let's say this is a circuit. Let's say this is machine A on the circuit, and there's machine B on the circuit. Now look at it. Voltage will have to first flow through machine A first before flowing to machine B. This is a series connection. If voltage has to go through one machine before getting to the other machine, then you have a series connection. But for a parallel connection, voltage can go to both machines simultaneously. Let me give you a diagram that represents a parallel connection. Let's say this is machine A, and this is machine B. If you notice, the current that flows to machine A doesn't have to flow to machine B. Let's say the voltage comes from this point. Some of the voltage goes into machine A, while some goes into machine B. So it means the voltage doesn't have to go through machine A before getting into machine B. So this is a parallel connection. And this is a series connection. Alright. So why does this matter? You don't understand a bit. For series connection, the equivalent inductance is equals to L1 plus L2 plus L3 plus all the inductors up to the last one, Ln. Just like AP and GP. This is for series connection. For parallel connection, 1 over Leq is going to be equals to 1 over L1 plus 1 over L2 plus 1 over L3 plus ... 1 over Ln. That's the last inductor in the circuit. Although the formula can get more advanced, when there is mutual inductance, but in all of those things, you don't understand them when we get to our class on, electricity, current electricity. So basically, this is what you need to know for now. If the circuit is a series circuit, this is the formula we use to calculate the equivalent inductance. If it's a parallel circuit, then this would be the formula. But now the question says, 3 inductors are connected in series, so our Leq is going to be L1 plus L2 plus L3. Why? It's a series connection. And the first, second, and third inductor has an inductance of 5, 10, and 15 millihenries. 5 plus 10 plus, is it 15 or 20? Yeah. Plus 20 millihenries at the same time. Which means the equivalent inductance is going to be equals to 35 millihenries. Yeah, for some of you that are shocked, how did Henry get into the conversation? Inductance is measured in henries. So the effective inductance or the equivalent inductance for this question is 35 millihenries. You could watch the video over and again till you get it. The next question is said, when a transformer has more secondary windings than primary windings. When do a transformer have secondary windings and primary windings? What is even a transformer in the first place? If I pick a coil, let's say this is a coil. Let's say this is a coil of wire. Yes. And I put another coil just close to this coil. And let's say I connect one of this coil to a source. Let's say a sinusoidal source and alternating current. A sinusoidal source means a source that supplies alternating current. If we remember Faraday's law of induction, because this inductor is connected to a source, current would flow. Now, the current flowing here is an alternating current, which means the current would go up and down. The current would be changing up, down, up, down. And if you remember Faraday's law of electromagnetic induction, you'd learn that when current flows through a conductor, there is always a magnetic field generated around it. Which means in the primary winding, because current is flowing from the sinusoidal source, you're going to be having a magnetic field generated in this primary winding that is going to be going up and down. So we're going to be having a changing magnetic field generated alongside the changing current in the primary winding. Are we together? Now, if I put the secondary winding in the presence or very close to the primary winding, because the primary winding is generating a changing magnetic field, an EMF is going to be induced in the secondary winding. And how do we know this is going to happen? Because Faraday's laws of induction says, if you have a conductor in the presence of a changing magnetic field, what is the changing magnetic field here? The magnetic field caused by the sinusoidal current in the primary winding. So let's say you put this secondary winding in the presence of this changing magnetic field. Because the magnetic field is changing relative to the conductor, an EMF is going to be induced in the secondary conductor. And if an EMF is induced, it means current would flow. Therefore, we are going to be having current flowing in the secondary conductor or in the secondary winding just because of the changing magnetic flux in the primary winding. And this concept is called something called mutual induction. It's where a primary coil induces magnetic flow of current into a secondary coil. This idea of mutual induction is the principle that transformers work on. Basically, this is a transformer. And what is a transformer supposed to do? A transformer is supposed to step up voltage or step down voltage. That's the job of a transformer. And how does a transformer step up voltage? One way you can step up the voltage in a transformer is to use something called a step-up transformer. What is a step-up transformer? A step-up transformer is a transformer that has more windings in the secondary coil than in the primary coil. So if there are more windings in the secondary coil than in the primary coil, then this is said to be a step-up transformer. Are we together? So it's going to increase voltage from the primary coil to the secondary coil. And what is the proof that having more windings will definitely increase voltage? Remember Faraday's law that told us the voltage induced is equals to N divided by T. If you remember this very, very well, N represents the number of turns. So if he has more turns in the secondary winding, then you can expect more voltage or more EMF in the secondary winding. Are we together? So the opposite of a step-up transformer is a step-down transformer. What is a step-down transformer? A step-down transformer is a transformer that has more turns in the primary winding than in the secondary winding. And the job is to reduce voltage. Does it make sense to you? Alright. Let's go on to the question. I said, when a transformer has more secondary windings than primary windings, automatically, because the secondary windings is more than the primary windings, or winding means number of turns anyway, because the primary transformer has less number of turns than the secondary transformer. Definitely, this is a step-up transformer. It means the job is to increase voltage. So which answer is most correct among A, B, C, D? Now option A is it has a smaller secondary current. This is the correct answer. Now I'll explain why this is the correct answer. In a transformer, we have something called an ideal transformer. An ideal transformer is a transformer whereby there is no flux lost. It has 100% flux linkage. What does flux linkage mean? The amount of magnetic flux that is induced by the primary winding into the secondary winding. Are we together? So the amount of magnetic flux that, that the primary winding induces into the secondary winding is called flux linkage. So in an ideal transformer, we have no flux lost to the environment. All transformer cannot be ideal. But basically, the most the transformer can do is move 100% magnetic flux into the secondary winding. That is the most. And at that point, it has 100% efficiency. What does this 100% efficiency also mean? It means the power supplied by the primary winding is going to be equal to the power in the secondary winding. That's what that 100% efficiency transformer means, or an ideal transformer. Most transformer would not be ideal. Most transformer would have quite a lot of flux lost to the environment. But this is where we are going to, let's even assume the transformer is an ideal transformer. It means the power input is going to be equal to the power what? Output. All together. So the power input is going to be equal to the power output. And in a situation whereby the power input is going to be equal to the power output, but don't forget, what is power? Current times voltage is going to be equal to current times voltage. But this is going to be for the secondary winding, and this is going to be for the primary winding. Watch this. If voltage increases, in the secondary winding, for the entire power to stay the same as the primary winding, current has to fall. Look at it. If 10 is equals to 10, and A times B gives us 10, but we have B increasing, for it to still remain as 10, A has to reduce. If not, it's going to be more than 10 because B has increased. Are we together? So for the power to remain the same, voltage will definitely increase because it's a step-up transformer. Therefore, current has to come down. Does it make sense? And that is for an 100% efficient transformer. What if the transformer is not even 100%? What if there is flux lost? Then we are going to be having power input is going to be greater than the power output. But this is where it now gets more assuring. If the power must come down, but voltage is going up, therefore current must come down very, very well. I don't know if it makes sense to you. So definitely, the right answer to this question is it has a smaller secondary current than primary current. Next question. It said PQRS is a rectangular cell with PQ perpendicular to the magnetic field as shown above. If a current flows in the direction of PQRS, in what direction will the coil move? This is very simple. There are three elements given to you. They're given to you magnetic field direction. Let me just write it B. They're giving us a magnetic field direction. They're giving us current, and they're looking for what? Motion or force. Don't forget, when you have three elements being given to you, then you know you're going to be applying Fleming's left-hand rule or right-hand rule. Any of them. Fleming's left or right-hand rule. In case you don't remember, FBI. We talked about this in our last class, Fleming's left-hand rule. Yeah, when do we apply left-hand rule? When do we apply right-hand rule? We apply left-hand rule to motors or motors. It depends on how you want to call it. Motors, both of them means the same thing. And we apply right-hand rule to generators. What is a motor? What is a motor? A motor is any machine that converts currents into motion. An example is a fan. It converts current into motion. And how do you know you are converting current into motion? Because they would ask you, what is the motion? This is what they are asking you to find, the motion. What about a generator? A generator converts motion into current. A very good example of this is something called a dynamo. A dynamo is a machine that converts movement into electric currents, still through electromagnetism. And what is going to be expected of you to find for generators? You're going to be asked to find the current. Good. Now go back to the question. They're asking us, in what direction will the coil move? So they're asking us to find the motion. And when we are looking for motion, automatically we are working with motors, which means we're going to be using Fleming's left-hand rule. And what does Fleming's left-hand rule says? The thumb is going to be facing the thumb will be the direction of motion. The index finger is going to represent the direction of the magnetic field. And the ring finger is going to be the direction of the what? Current. FBI. All of these are perpendicular to each other. Alright. So, where are we? Because the current in the question is flowing in this direction, let's go back to it. Look at it, the current is coming from P to Q, then Q to R. So the current is flowing in this direction. Watch my arrow, in that direction. If you apply Fleming's left-hand rule, then the motion will be what? Upwards. Does it make sense? Very, very, very good. So the right answer here is upwards. The next question. Yeah, they said a step-down transformer is used on a 2.2 kilovolt line to deliver 110 volts. How many turns are on the primary winding if the secondary winding has 25 turns? Yeah, for transformers, there's a relationship you need to understand. The relationship that exists between voltage and number of turns. And what is this relationship? The relationship can be written in any of these two ways. The voltage of the primary winding divided by the voltage of the secondary winding is going to be equal to the number of turns in the primary winding over the number of turns in the secondary winding. That is the ratio of the voltage generated in the primary winding to the secondary winding would be the same as the ratio of the number of turns in the primary winding or the secondary winding. Another way we can state this relationship is the voltage in the primary winding to the number of turns in the primary winding is going to be equal to the ratio of the voltage in the secondary winding to the number of turns in the secondary winding. These two relationship works for voltage and number of turns. So we can pick any of them for this question. We are told that the primary voltage is going to be 2.2 kilovolts. So let's call it 2,200 volts because that's what kilovolts basically means. Secondary voltage is 110 volts. Number of turns on the primary winding unknown. That's what we are asked to look for. But number of turns on the secondary winding is 25. So how do we go about this? Pick the relationship. So I could say 2,200 volts over 110 volts is going to be equals to X over 25. Cross multiply and divide. I'm going to be having 2,200 times 25 is going to be equals to 110x. Divide both sides by 110. Press your calculator. So we have 2,200 times 25. 2,200 times 25 divided by 110. The answer is 500 tons. Therefore, X is equals to 500 tons. Very easy. Replay the video as many times as possible till you get your explanation the way you want it. Okay, a generator manufacturing company accidentally made an AC generator instead of a DC generator. To fix this error, what do you do? Keep it in your mind. And a DC generator is more or less a motor. And the motor makes use of something called split rings. While an AC generator makes use of something called slip rings. Let me write it for you. Motors or DC generator make use of split rings. I talked about split rings in our last class. It's a device that reverses the flow of current, isn't it? Every time the armature rolls 180 degrees. Check out our previous video, our previous class, and you understand what split rings do. But for generators, AC generators, instead of split rings, they use slip rings. So if I've made a DC gen instead of an AC gen, all I have to do is replace the split ring with the slip ring. Easy. Okay, this one, they made an AC instead of a DC. So it means you're going to be replacing slip with slip. You're going to be replacing this with that. Does it make sense? Easy. I said, which of the following operates based on the magnetic effect of electric current? I just explained this, a dynamo. A dynamo converts motion into electric current, through the magnetic field of the electric current. It basically follows the law of electromagnetic induction. So the answer is dynamo. In case you don't know what a dynamo is, make your research and search for what a dynamo is. Then you understand that. Now they said if a charged ion goes through a combined electric field and a magnetic field, E and B respectively, the resultant emergent velocity of the ion is going to be. Let's go over the calculation of this. So I know we've not done electrostatics together, but for some of you, you've done it before. The electric field generated by a point charge is given as F over Q. Electric force over quantity of charge, So when we cross multiply, I could say F is equals to AQ. Let me call this equation 1. Also, we know that if I put a point charge in a magnetic field, it feels a Lorentz force that is equals to QVB sine theta. Let's just say QVB. If theta is equals to 90. Or let me even make it easy. It feels a maximum force of QVB. Are we together? A maximum force of QVB. And how do we know it's maximum? Because theta is going to be equals to 90 degrees. So that sine theta can be 1. Basically. If you don't remember this, check our last class. I can equate equation 1 and equation 2 together, and I'm going to be having EQ is equals to QVB. Divide both sides by Q. I'm going to be having E is equals to VB. So to make velocity stand alone, divide both sides by B. And velocity is going to be equals to E over B. Option A. The next question. It said an ideal transformer, we've done this, has no flux leakage. No flux is lost to the environment. So that's what an ideal transformer is. No flux leakage. 100% efficiency. Which of the following measuring instruments operates based on the effect of electric current? Well, this is easy. The answer is hot wire ammeter. Some of you are thinking electric heater. Well, electric heater works on the principle of resistance, on Ohm's law. You put an high resistance, high resistor inside a circuit, so I'm going to be generating a lot of heat. A hot wire meter works by generating the heat in a current to determine if current is flowing inside. What am I saying? Hot wire ammeter measures the current flowing in a wire by evaluating the heat inside the wire. If the wire is hot, it means, current is flowing through the wire. If the wire isn't, then current isn't flowing. So you could measure the amount of current by the level of heat. And the answer is hot wire ammeter. This is the correct answer. As per Faraday's law of electromagnetic action, an EMF is induced in a conductor whenever, if you remember Faraday's law, it has to cut magnetic flux. How do we know it has to cut magnetic flux? Because the conductor has to move relative to the magnetic field. The conductor moving is going to start, interfering with some of the magnetic flux, which will generate what? EMF. Did you understand it? So that's why the answer is cut magnetic flux. Does it make sense? And the last question, they said the device that operates using the magnetic effect of electric current is, the answer is an electric bell. How does an electric bell work? Whenever you press the switch of an electric bell, current would flow inside a circuit. And don't forget, when current flows, a magnetic field is generated around the current, isn't it? Now, inside the bell, there is a spring connected to an iron bar and an hammer. Now, when current is flowing inside the circuit, the circuit would attract, the iron bar attached to the spring. Because it's attracting the iron bar attached to the spring would stretch, and the hammer attached to the spring would strike a bell. And once current leaves, the magnetic force would leave and it would release it. So the constant flow and disconnection of electricity would cause, the magnet to keep attracting and leaving the hammer, causing the hammer to strike the bell repeatedly. And that's how the bell rings. For you to understand it, you could watch YouTube videos on how an electric bell works. And you're going to understand that it just works based on the magnetic effect of electric current. We've attended all the questions, and we'll call it a day for today's class. See you in our next class. Take care and God bless. Bye.